Hi, in this video, we want to take a look at forecasting autoregressive time series. All right, so in this video, we're going to take very much a linear regression point of view in trying to forecast the future values of a time series. Now, we're only going to focus on autoregressive processes, so we're not going to worry about moving averages or anything more exotic. And this is going to very much feel like an ordinary least squares discussion on forecasting. All right, so let's talk about where I'm getting this from. So we're running through some examples from time series analysis and its application. Here are the authors' names. Here's their GitHub page. And UCF students can download this textbook for free through the library. So now let's actually get down to it. All right, so our goal is to predict the future using our observed values of data. So what we're going to do, we're going to take the observed values of our time series, and we want to predict some point in the future. All right, so N is going to be the number of observed data points I have for my time series, and M is how many steps out into the future that I want. So let's say that I have a time series that is monthly. Next month would be M1. If I have a time series of daily and I want to predict a week from today, M would be 7. Or if I want to do next year, M would be 365. Now, if I have a yearly time series, next year would be M equals 1. Now, something that's important about this video is that we're going to assume that our time series is stationary. And as we're working through this, we're going to go, when it's necessary, we're going to say that model parameters are known because we're taking a theory point of view for the most part in this video. Now, the minimum mean squared error predictor, what we're going to do is we're going to say, hey, I want the value that will give me the minimum mean squared error, and that's going to be my predictor. Okay, well, why would we want that? Well, we know that the minimum mean squared error would just be that's minimizing a measurement of the mistakes in my model. All right, well, if you remember from your stat theory class in the past, you'll remember that if I have the expected value, my observed value, minus the expected squared, then take the expected value, looks a lot like variance, right? That will be less than or equal to any other function I could put my time series observed values into, subtract the difference from observed, square it, and then take the expected value. So the difference squared expected value with the expected value will be less than the difference squared expected value for any other function I could drop my time series observed values into. And so for now, we're going to take a look at just using this. So we want to use the expected value of our future value of the time series from conditioning on our observed data. Okay, so we're going to approach this using linear predictors, just like we would with linear regression. Okay, so why do we do that? The theory works out well, and these perform pretty well for their purpose. All right, so linear predictors only depend on the first and second moments of a process. And what we're going to do in this notation, I'm saying that I have n observations, and this is the observation in the future I want to forecast, I want to predict. And what we're going to do, I'm going to take coefficients times my observed data, 1 through n, add on a constant, and that's going to be my linear predictor. The alphas are coefficients, they're constants, and it's the value of our that we observe is getting multiplied by the coefficients. Now, something that's important is that the coefficients depend on n and m. All right, so if n is equal to 1, m is equal to 1, this is a one step ahead process. x12, my linear predictor is going to be a constant plus a coefficient times my one observed value. Now let's say I want one step ahead, but this time I have two observations to work with, and I want to do one step ahead like before. So this is x23. My linear predictor is going to be the constant alpha 1 times x1 plus alpha 2 times x2. It's going to work out that more than likely, this alpha 0, this intercept, is different than this intercept. This coefficient, even though it's written the same way in the model, is different than that coefficient because I have additional information to work with. So in general, the coefficients for different predictors, depending on different observed values, will be different. Now, let's talk about the best linear predictors. In statistics, when we say best, we mean minimum variance. All right, so anytime you see best, if it's an estimator, immediately think minimum variance. So linear predictors that minimize the mean squared predictors are called the best linear predictors. All right, so now we're going to get into some meatiness. Now, here's the exciting part. We're going to get into some theory about regression, and we're going to do the projection theorem. All right, so let's say that we're dealing in a Hilbert space. All right, so this is a very, very mathematical theory aspect that we're taking. This is our point of view. All right, a Hilbert space is a complete normed vector space with a dot product. Okay, let me go over that. It's a complete normed vector space with a dot product. Vectors, or a vector space. We're taking the most mathematically general point of view of what is a vector. So a vector, if I add two vectors from a space, they're also inside the vector space. If I take a scalar and multiply it by any vector in the vector space, the product is inside that vector space. That is what a vector space is. And also 0 is inside the vector space, the 0 vector. Now, that is what vector space is. Complete well, actually, I should say norm. So also a Hilbert space is a normed vector space, not just a vector space, it's a normed vector space, which means it has a norm of measuring the distance between two different vectors. Now, that doesn't sound like a big deal, but the norm has to satisfy like the triangle inequality. It's equal to 0 only if it's if the norm is equal to 0 only if it's 0, things like that. Now, the next one is complete. Complete means that Cauchy sequences that converge to 0 have a point that they converge to within the space. All right, those three items there, complete normed vector space, is what makes up a Banach space. Now, the Hilbert space is a Banach space with a dot product. Okay, and so a dot product is an operation on any two elements of the space that is mapped to the real numbers or the complex numbers, depending on what you're working on. For us, we're going to keep it real, yo. So real numbers. So H is our Hilbert space. So it's a vector space with a dot product. That's what we need for the moment. We're going to have a closed subspace of our Hilbert space. Then, now here's the theorem itself. For any y in the Hilbert space, there exists a unique y hat in the closed subspace such that, excuse me, there exists a unique y in the closed subspace and a unique z outside of the closed space such that these three things happen. All right, so y is equal to y hat plus z, and this is a unique representation. The dot product between z and any element of M is equal to 0, and y minus y hat in norm is less than y minus any other vector in the closed subspace. All right, so why is this important? what we're going to do is that we're going to say that what we're trying to forecast is y, okay? And what we have, M, is the vector space that is spanned by our observed data. All right, so M is all the possibilities that I can get from my observed data. I want the best approximation I can of something that's outside the span of my data. And this makes perfect sense because if I'm trying to forecast, that's the future. I don't have it observed. This is outside the span of my observed data. So the three things that we're going for. First one, we have a unique best representation. So this one is a unique representation. This one states that there's nothing left to give. There's nothing else I could pull in within the closed subspace. And this is saying that it's the best one I can get because it's minimizing that norm difference. All right, so first and foremost, so for the projection theorem, if y is equal to m, then y hat is equal to y, z is equal to 0. We're done with the proof. Now let's get into some meatiness. If y is not in m, what I'm going to do is I'm going to let delta equal the infimum of the norm of the difference between m and y. So remember, y is outside of m. I'm going to look at y minus all possible vectors inside that closed subspace. I'm going to subtract, take the norm. All right, I'm going to set delta equal to the infimum of them. So think minimum for the moment. If you're not comfortable with the infimum, think minimum. Now, if you've taken real analysis, you know that infimum, we can always take an infimum, but minimums may not happen. It ends up that this is going to be a minimum, but we need to show that in the proof. All right, so as an infimum, there exists a sequence v sub n such that the norm with that sequence converges to delta. All right, so there's a sequence. And by saying that, either I have convergence so that this is actually equal to it, or I have an infinite series that they're getting arbitrarily close to delta in this. All right, so what I'm going to do, I'm going to select. So if it converges, what I would do, I would just take what I want and I'm good, but I haven't proved that that happens. If it happens, my sequence is just going to be repeating that same converged value over and over and over. If I don't have convergence at this point, what I'm going to do, I'm going to select all of these v sub n's. I'm going to take the infinite sequence so that this normed squared is less than or equal to delta squared plus 1 over n. Now, why am I picking delta squared plus 1 over n? Well, because I've already looked through this, worked through this problem. I know that that's going to work for future upcoming steps. All right, so now what I need to do, I need to show that v sub n is in fact a Cauchy sequence. Why do I want that? Because if it's a Cauchy sequence, I'm in a complete vector space. It's Cauchy means it has something that converges to. What it converges to is going to end up being our best estimator of y. All right, so since v sub n and v sub m for any two in our in our sequence are in m, it's going to work out that y minus the average between the two squared has to be greater than or equal to delta squared. Why is that? Well, remember that delta is the infimum. This is the smallest possible value I could get from all possible vectors. Well, if this is the smallest possible value I could get from all vectors in M, if I take any other one besides that, it has to be greater than or equal to it. So I know that this norm has to be greater than or equal to delta. And I've got the square on there. Okay, so now why am I working with squares? So that way I don't have to really do as much work with it. So now remember, with dot products and norms, the dot product is equal to the norm squared if I take the dot product of an item with itself. All right, so here I'm going to take the norm squared, which is the dot product of Vn minus Vm with itself. Well, here, notice that I effectively add and subtract y to itself. Here I'm subtracting y, here I'm adding y. Adding and subtracting the same item is equivalent to adding 0. And so, just using the dot product norm relationship, I know that I have this line of my proof. So now there is a fundamental result that this is equal to all of this. Okay, so notice that what I'm doing is I'm basically just rewriting the norm in another manner. It looks ugly, but everything's going to work out right. Because you'll notice I have this twice. I have this twice. And then I have this part, which we talked about a moment ago, left over. And we have a lower bound on that. Okay, so now this line is just cleaning up the equation. Well, I know, all right, so from my selection of v sub n's, I know that I have an upper bound of delta squared plus 1 over n. I'm going to replace this norm with this. It's an upper bound. I'm going to replace this with the corresponding upper bound. Now, this part here, I've got a negative sign. Well, subtraction, what I'm going to do, I'm going to say, well, what's the least thing I could possibly subtract off? And because I'm trying to get an upper bound on this. So when I do that, I'm going to replace this with delta squared. And so now all of these I have found an upper bound for. I found an upper bound on this. I found an upper bound on this. I found a lower bound, but the negative sign, that lower bound with the negative sign becomes an upper bound. And so now I know that all of this is less than or equal to this. So now I'm just going to write it out. Hey, look at that. Now, when I look at this, I know that this norm squared is less than or equal to that. Well, what's going to happen as n and m go to infinity? That goes to 0. Cauchy sequence. All right, so we have a Cauchy sequence. I'm in a complete normed vector space, which means the Cauchy sequence has something that converges on. All right, so now I'm going to take that, and I'm going to say that is my predictor of y. This is why we care about it from a statistics point of view. All right, so I'm going to say that y hat is what this sequence, Cauchy sequence, converges to. So now I have a predictor to grab onto. Now I want to show its other properties. I want to show that it's the minimum, and I want to show that it's unique. So I want the minimum norm property, and and this also shows minimum norm also. So we worked out the minimum norm aspect by working this out. For uniqueness, what I do, I just say that, what if there were two different, vectors to work with? Well, I would do the same trick. It's honestly just the same trick. I say I have y1, y2, do the subtraction, I work it out. We get a bound on delta, and then boom, we got it. It's kind of boring. All right, so now we need to show that y minus y hat is orthogonal to everything that's in M. So what this is saying from a statistics point of view is that once I have my predictor, there's nothing more I can squeeze out of my data. There's nothing left for me to get of informative value once I have my y hat. That's how we're interpreting orthogonal. So we want to show that y minus y hat is orthogonal to everything in our closed subspace. All right, so let's let y sub 0 be any length 1 vector in M. Okay, well then let's say if that's any length 1 vector, then its entire span can be represented with alpha times y sub 0. Okay, so if there is something I could possibly get out of my out of M after I found y hat, there's some informative value somewhere floating around there. What I could do is I could represent it as its length 1 version and then multiply by a scalar. Okay, so what I want to do is I want to play the game like, you know what, let's just go ahead and just pretend that I'm going to go ahead and just tack this on and see if I can do better. Can I do better than y hat? All right, well, so what I'm going to do is I'm going to take the dot product. I need to minimize this because that's the norm squared. All right, using the dot product properties, I just expand this out, and you'll notice that quickly I get a quadratic equation on the scalar of y sub 0. Well, it's a degree 2 polynomial on alpha. Let's go ahead and minimize that. Remember, negative b over 2a from your degree 2 polynomial is your quadratic equation. All right, I'm going to invoke that, where here this is a, negative 2 times this dot product is b, and here is c from college algebra. All right, so I know to minimize this norm, I need to minimize this degree 2 polynomial. So I set alpha equal to negative b over 2a, which is equal to that. Now the rest of this is me just crunching it out. I'm just going through and just crunching, getting this through until we have what we get. So what I'm doing, I know from quadratic equation the minimum, the alpha that will give me the minimum possible value, and it's going to work out that the minimum is when alpha equals 0. All right, so we will skip some of the details to focus on the meat and potatoes of what's going on. So now what I want to do, I want to look at covariance as our dot product. All right, so what we're going to do, we're going to say that the expected value of x minus its expected value, y minus its expected value, is going to be our dot product. Without loss of generality, we're going to proceed assuming that mu sub x and mu sub y are equal to 0 just for ease of notation. When we need to, we'll bounce back to non-zero cases. All right, so now we want to take a look at a Gaussian process. Now, for a Gaussian process, the minimum mean squared error prediction is the best linear predictor. So the projection is the expected value, is the punchline. All right, so what we want to do, we want to show that that expected value we were just talking about is equal to the projection we were just talking about a moment ago. All right, so what we're going to do, we're going to say that y and then all of our observed values, this should be a subscript in, is multivariate normal. And we want to show that the expected value of y given all of our observed data is equal to the projection of y onto the span of our observed data. So now let's do the proof. Let's say that y hat is equal to the expected value of y given, or the expected value of y over the closed subspace. All right, well, This is going to be that unique element from the projection theorem, and it's going to satisfy that dot product aspect is going to be equal to 0. So any other vector in the closed subspace, if I take y minus that expected value, multiply by any element inside the closed subspace, and then take the expected value, I'm going to get 0. Our goal is to show that this expected value is equal to the projection of multivariate y, multivariate normal's y component onto the multivariate normal observed data. All right, so now if I say, if we let y hat equal the projection of y onto all these guys, then from the orthogonal principal aspect, we know that this is going to be equal to 0 for all x of I because of the orthogonality. Now, what I'm going to do is y with all of the x's, x of 0 is equal to 1, is going to be multivariate normal. If I subtract off a constant, so at this point, once we've established our spaces, y hat is a constant, subtracting that off does not change the class of the distribution. So this is still multivariate normal. Thus, 0 covariance gives us independence between y minus y hat and x of I. So when we're dealing with multivariate normal, 0 covariance is equivalent to being independent. In general, independence implies 0 covariance, but 0 covariance does not imply independence. It does in the special situation of multivariate normal. All right, so now from independence, we can factor covariance into expected values. All right, well, 0 is equal to my dot product here, but I know that this expected value is equal to the product of expected values because of independence. Okay, well, one of these has to be equal to 0 for this to work out. And this equation works for any w in the span, so I know the expected value of y minus y hat has to be equal to 0. And so the expected value of y minus y hat is equal to 0. Therefore, y hat is equal to the expected value of y. So boom, we have that the projection and the expected value are in fact equal to each other. All right, so now let's look at the best linear predictor for stationary processes. All right, so this is going to give us our prediction equations. Given that I have some observations, x1 through xn, the coefficients of the best linear predictor are going to solve this expected value equation. So from all the work we've just done with all of those expected values equal 0 stuff, I know that the best linear predictor of all the possible coefficients I could be using, I want the coefficients so that when I get these values here and I drop them into this expected value, I will get 0 for every single k, 0 through n. All right, so now this gives us a way to find out what are these coefficients. All right, so what we're going to do is I'm going to take the observed value minus the linear predictor, and notice I pulled in the 0 on this one. Here, k is equal to 1. Here, k is equal to 0, just to make it a little bit cleaner. All right, so here I have expected value squared. So what I'm going to do, if I want to minimize, I'm going to do exactly what you would do in any other situation. I'm going to take a derivative set equal to 0, find it, boom. Okay, so now here, what I'm going to do, this works out nicely that I know that the covariance is equal to 0. And I can use that here to figure out my very first predictor. And we can start slugging this out. So what I'm going to do, I'm going to set k equal to 0, which gives me 1 for x sub 0. Well, then that's a constant, and multiply by 1 does nothing. All right, well, so then I'm going to just start, working with my expected values here. I know that's going to be equal to mu. Well, this is my predictor here. So I know that the expected value of my predictor is equal to the expected value of what I'm trying to predict, mu. So I know that the expected value of my predictor is equal to mu. And so now that's constant. Coefficients are constant. Taking expected value, that's expected values on x sub k, which, because it's stationary time series, is going to be equal to mu itself. And so now I just solve for alpha sub 0. Now I know alpha sub 0, and I can take that, plug that into what's going on, and now I have a little bit cleaner of a notation. I have one less thing to worry about. And so the best linear predictor is going to be the mean of my time series plus coefficients times observed values minus their expected value. All right, so now let's look at the one step ahead predictions. Given that we have these values are observed, we want to predict the next one. So we want to do one step ahead. All right, so without loss of generality, we're going to say that mu is equal to 0, and it's going to follow that alpha sub 0 is equal to 0 also. And so I'm doing this just to make things easier. If that's not the case, when I'm actually modeling, I'll just do a shift to get what I want. All right, so what we're going to do, I'm going to take my endpoints of data, and I want to forecast one step ahead into the future. And we're going to change the notation just a little bit because we're going into the situation where we're going to consider different sets of observed values. So at time 1, I have 1 observed value. Time 2, I have 2 observed values. Time 3, I have 3 observed values. And so n is going to be the number of observed values I have at that time. For all the situations, though, we're only considering one step ahead. And so here, what we're doing is I've got a coefficient times a lagged observation. All right, well, I know from that from the equation we just looked at a moment ago, if I take the value I'm trying to predict, I subtract my predictor off of it here, and then I multiply by lagged variable, the expected covariance will be equal to 0 every single time. Okay, well, let's take advantage of that. I'm going to go ahead and I'm going to just distribute lagged variable across, and then I'm just going to rework the expected values. All right, so here I have future value and lag value. I look at that and go, hey, expected value of the product of two things, that's the covariance, because remember we have expected value of 0. That's my covariance over here. I look over here, and once again, hey, that's another covariance. All right, so now I've got an equation. Covariance of k is equal to the covariance of k minus j times coefficient and then summation. And this has to work for all k's. All right, so now I have a whole bunch of these guys. So let's go ahead and write this in matrix form. So I'm going to say gamma sub n times phi sub n is equal to little gamma sub n. All right, so gamma sub n, its ith jth entry is little gamma K minus J. This will be an n by n matrix. It will be symmetric. And we're going to say that phi sub n is equal to a vector of the coefficients. And then little gamma is a vector of covariances. All right, so big gamma is a symmetric matrix and thus semi-positive definite. Why is it symmetric? Because the little gamma of 1 and little gamma of -1 is in fact the same value. So we have semi-positive definite. Now, if big gamma is singular, there are going to be infinitely many solutions for the coefficients. But by the projection theorem, our actual predicted value will be unique. So here, something this is really cool, this doesn't come up very often in mathematics, is that I could have a singular non-invertible matrix and I still get the result I want. I don't have to worry about the details in between. So here, this is one of the few times in math it's okay for it to not be invertible. That's as exciting. All right, because no matter what happens, by the projection theorem, my value that I will be predicting with, my estimator, will be unique. Now, it's going to work out that if big gamma is non-singular, then phi is going to be unique. Now, mathematically, when we're dealing with randomness, random values, if I'm actually dealing with like multivariate normals type stuff, it's almost guaranteed to not be singular. So in general, in real life data, we don't have to worry about the singular case. So for most situations that we would find ourselves in with real data, where we have variance greater than 0, and we have the covariance converging to 0 as h gets large, the big gamma is going to be invertible almost surely. All right, so, well, now I'm going to just apply matrix notation, and this is going to be my estimator. I'm going to take really the dot product between the phi vector and my observed data vector. And so now let's go ahead and get the mean squared one step ahead prediction error. I'll leave that here. All right, so what we're going to do, I'm going to take value I want to predict minus my predictor. I'm going to square it, take the expected value. And so then this is my computation, my matrix notation from up here. All right, well, this, I'm going to replace phi with this. Notice that it is a transpose on the phi, so I can do the matrix multiplication. And so I change the order and take a transpose. All right, so now I know that I've got matrix multiplication inside my expected value. So I have to do a little bit of fussing with it. If you've taken a theory course for linear regression, you'll know that this, I need to rewrite in this format. And then I just start plugging and chugging the right way to get this going. And you'll notice that here I have a covariance. Here I have x times its transpose. And so now I realize that this, I'm taking an expected value of my time series with itself. So that's going to be, in fact, the variance here. This is just going to connect to little gamma. And this gets replaced by big gamma. Well, big gamma will cancel out with the inverse. And I notice I have, after I do this cancellation, I have the same thing twice, but one of them has a -2. And so all that cancels out. And so now I have my prediction error. Nice, nice. The mean squared prediction error is worked out here. All right, so now let's go ahead and verify that the matrix equations gives us the correct coefficients with an autoregressive process on 2. All right, so let's say that this is my true process. The x of t is equal to phi 1 times previous value, phi2 times 2 steps back, plus my white noise. All right, so from the equations we just looked at, phi sub n, the coefficient vector, is equal to big gamma inverse times little gamma vector. And I can sit down and start working it out. Phi11 is just going to be equal to, this is big gamma inverse, and this is just gamma sub n. And so I end up getting, I realize that this is just the autocorrelation of a lag of 1. And so then here I got my predictor. Okay. Now, if I want one step ahead with 2 observations, so what we just looked at was just with 1 observation, when I have 2, then I'm just going to go ahead and do the matrix equations. And so here, take the matrix equations. I plug in for phi vector. I plug in for gamma vector. And I plug in the inverse of big gamma. Well, it's the inverse of a 2 by 2 matrix. Easiest inverse to do ever. And, we just switch A and D, make B and C negative, and then we divide by the determinant. And so we get that result. So now that's the matrix form. Let's back this up for a moment, and let's think about the AR2 process that we have. Let's focus just on the AR2. All right, so what I'm going to do, here's my x sub 3. Here is my best predictor possible. Realize that x sub 2, x sub 1 are observed. Phi1, phi2 are constants. If I subtract x sub 3 minus my best predictor, that's going to in fact be a white noise term. And if I take white noise, multiply it by observed value, expected value, I'm going to get 0. White noise times observed data, expected value will be equal to 0. So I can take that. I know that this white noise is equal to this, the difference between observed and predictor. And so now I see that I've got orthogonality between observed data and predictor and the value I'm trying to predict. All right, so by the uniqueness aspect of coefficients in the situation, I know that the phi here is equal to the phis here. They have to be equal to each other. And so I know that I'm getting the same value regardless of how I approach this. And so if I keep slugging through this, I repeat this, but I do it for later observed values in the time series, I'm going to see that every single time, the matrix coefficients are going to end up giving me exactly the values I'm supposed to get. And so we can extend our computations to see that the best predictor I could possibly have is if I knew the true coefficients, the best predictor I could have one step ahead for an AR process would be the coefficients from the process times my lag variable, add them up, and that would give me the best one step ahead predictor possible. This is intuitively obvious that if I had a time series process, autoregressive, and I just took my lag variables and multiplied by the actual coefficients, I would get the best predictor possible. That's intuitively clear, but up until now, we didn't show that it was true. Here, now, we know this is the best way possible. All right, well, life is short. Do math.